Now, good morning, everybody. Thank you, Ernesto. Thank you, Patrick. All right. Thank you, Matthew. Today, it's going to be a short session. I will only uh, talk about logarithm and then dismiss the class. That pretty much will take care of chapter 13. And next week and next Tuesday, I will start chapter 14. Okay. Do you have any question about previous topics so far? No question. Right. Perfect. Thank you, Patrick. All right. So let me go to my whiteboard. Yeah, this is what I'm supposed to do today. 13.7 and 14.1, but I will skip. I will, just do 13.7, which is logarithm, okay? In chapter 13, by the way, the question is, what have we done? It is good to know overall what is being covered, what are the topics that we discussed. Well, we started with complex numbers and we tried to establish some sort of algebra within complex numbers, all right? And of course, uh, the geometric interpretation of complex number and different representation of complex numbers, which the most important one, of course, was the polar representation or exponential representation. Well, I introduced several functions, including exponential function e to the z. I introduced trig functions in complex. And the difference between uh, exponential functions of complex and the exponential function that we saw in calculus, and that's important. Always, although a lot of uh, rules just will apply here. But there are differences. Please, as soon as you see something, for example, as soon as you see uh, trig function sine z, just justify for yourself. Yeah, that is true that all those identities will be valid. But there is a difference between sine z when z is complex and sine x when x is a real number, right? There's a difference between the calculus and this complex here. Anyways, last time I started by introducing logarithm, and here is how it goes. So after learning about exponential function, now the question is, if we are given a complex number, right, like this, we can write it in polar format. Can we find a w that e to the w be this one? Well, of course, e to the w, we know it is a complex number, u plus iv. And after examining this equation, we notice that, look, this r is just uh, this w, which is complex number, u, the real part, is just natural log of r. And then how about v? Well, e to the iv will be e to the I theta. And whenever, oh, here is one of the very important differences between an exponential function in complex and exponential function in calculus. In calculus, if you have such a thing, right away you say IV equal I theta. But we cannot do that in complex. It complex, it V or IV will be I theta plus 2k pi I, k being an integer, all right? So in this fashion, we also found V. So we have U and V. This W, that in a way is inverse of exponential, this W, we call it logarithm of Z. And from now on, logarithm of Z is denoted by this. Okay? This is, in fact, this W is what we call log of Z. What is Z? Here, Z is R e to the I theta. Okay? So this is called, in this case, you see, we are going to have infinitely many results for the W. So log of Z is not a single value, does not produce just one quantity. It produces infinitely many depending on that K. But if we want to make it single valued, we choose this part. This is the crucial part. We choose that one to be the principal argument, all right? The principal, and we call it the principal branch of complex logarithm. And we denote it by this uppercase L. So it is natural log of R plus I theta, theta being the principal argument. And I gave you a bunch of examples as how to find logarithm in complex, all right? You just follow this. You have this complex number 1 plus I. Here is 1 plus I. Its modulus is the square root of 2. Its principal argument is pi over 4. So logarithm of 1 plus I will be natural log of this. This is a real number, pi over 4I. Okay. All right. Now, of course, next we want to find the properties of logarithm, all right? And one of the properties this sort of indicates that they are, in a way, inverse of each other, logarithm and exponential function. But there is a little difference. Yeah, it is true that e to the log z is z. But the logarithm of e to the z is not exactly z. You get 2k pi I attached to it, all right? unless you want to consider the principal argument, then logarithm of e to the z will be z. So here are, well, that example was done earlier, but the difference between this example and the previous one is that here we are not talking about principal branch. We are talking about, in general, logarithm of 1 plus I, and you always have that 2k pi I attached to it, all right? So this is all values of log of 1 plus I. But in previous example, we just had principal value. Here's another example. Look, this is interesting. Here's -3. By the way, in calculus, logarithm doesn't make sense for negative quantities. Doesn't make sense, right? But in complex, we can have log of -3. How? Oh, well, here is -3 in coordinate axis. And the argument here, remember the argument is the measured counterclockwise from x-axis. So here is, for instance, pi over 4. Going a little bit over, here is pi over 2. And when it comes to this negative direction of x-axis, the argument or principal of argument is pi. Okay, pi. And the modulus is 3. So all values is logarithm, its modulus, plus I. Remember, pi is the principal argument, and 2k pi I. Okay. Oh, here is another example. Why not? Because in your next test, I'm going to ask you to find a logarithm of certain quantities, certain complex numbers. It's good to be good at it. So -1, -I. Well, please note, I am talking about principal argument, logarithm. Uppercase L. So here is -1, -I. The principal argument is -3 pi over 4 from here to here. Its modulus is square root of 2. So the principal value of log of -1, -I is natural log of a square root of 2 minus I theta, and theta in this case is 3 pi, -3 pi over 4. Okay, good. Well, when it comes to rules of or properties, you remember these two properties from pre-calculus. They are still valid here, but they might not be valid for principal argument. In general, it is true for natural log, all right, but not. It might not be valid for principal branch of logarithm. Okay, Well, next thing to talk about is sort of dealing with derivative, right? Why not? After being able to um, find logarithm, let's find derivative. Well, so here is a log function, and I cannot talk about derivative for a function that has a lot of values. So we need a single valued function to talk about its derivative, all right? So, and the single valued function here would be principal branch. So the principal branch is this. If z is r e to the I theta, log of z is natural log of r plus I theta. So if you think about u plus iv, here is u plus iv. This is the real part. This is the imaginary part. Well, oh yeah, I have it right there, so I don't need to do it twice. The question is, if we write it in this fashion, does it have derivative? Well, remember Cauchy-Riemann equation and its inverse? If the function satisfies Cauchy-Riemann equation and the real part and imaginary part are continuous and have continuous partial derivatives, then we can say, yes, it has a derivative. Well, here I need to express this Cauchy-Riemann equation in polar. Cauchy-Riemann equations in polar are these. And if the function has derivative and satisfies Cauchy-Riemann equation and those conditions, then derivative will be e to the negative I theta u sub r plus iv sub r. Then I will talk about that momentarily. So here is the u, here is v. What is partial derivative of u with respect to r? Oh, derivative, this is real. This is calculus right here. So it will be 1 over r. What is derivative of u with respect to theta? Oh, there is no theta here, so it will be 0. Oh, let's look at v. What is derivative of v with respect to r? There is no r, so it's 0. With respect to theta, it's on. Well, do we have Cauchy-Riemann equations? Well, look at this second equation. V sub r, which is here, is this number times u sub theta. Oh yeah, both sides will be 0. So this part is good. How about this first equation? U sub r is 1 over r times v sub theta. Yes. So Cauchy-Riemann equations in polar format, they are satisfied. Now, if we have such a thing, then derivative, after, of course, looking at the conditions, derivative exists and is equal to this one, e negative I theta. U sub r is right here, 1 over r. V sub r is 0, so it will be 1 over r times this, bring this down. So this is exactly z. So it is 1 over z. So what happened, I proved that if derivative exists for logarithm, derivative is 1 over z, okay? Derivative is 1 over z. But we need to verify the condition that whether this u and v are continuous or not. All right, u and v are continuous or not. I'll talk about that momentarily. But for the time being, remember, I am talking about the principal value because we want this a function that for any input produces one output. That is called single valued function. And I went through Cauchy-Riemann equations in polar, and I noticed that the derivative of this guy exists is 1 over z, provided we have that continuity condition. All right. Now the question is, do we really have that continuity condition? Well, okay. So let's check on that one. If the continuity condition holds, then this is true. Well, the real part was theta. Okay, I'm just going to examine that continuity, and then I will come back to some. Okay. So before talking about continuity, remember logarithm. Definition of logarithm is this. So log of z is log of r, which is modulus of z, times I theta. The question that I want to examine, yeah, this one is fine, but this one, is this continuous? Remember, we are talking about the principal argument theta has to be between negative pi and pi. The answer is, oh, this is a fairly good function, right? So for each z, the output is its principal argument. The question is, such a function, is such a function continuous? Well, unfortunately, it is continuous everywhere except along the negative direction of x-axis. And here is why. Suppose this point is on the negative direction of x-axis right here. You can approach this point from two different directions. You can approach here from by staying in second quadrant. If you stay here, look, the principal argument is this, and you get closer, and you get closer. So if you approach this point, take limit as z approaches to this point, the limit is pi, right? Because this is the principal argument, and you get pi. But if you stay in the third quadrant and approach this point, the principal argument is this. Okay, always principal argument is between negative pi and pi. And if you take a limit while staying in third quadrant as z approaches z naught, then limit will be negative pi. Okay, so limit does not exist because we are approaching that point from two different directions and we are producing two different numbers. So the limit does not exist. As a result, the function is not continuous. Okay, so what is the conclusion? The conclusion is logarithm principal branch of logarithm has derivative everywhere except on the negative direction of z-axis. Of course, doesn't have derivative as zero either. All right. So this because we don't have continuity of this imaginary part. Okay. All right. This is called a branch card. We can talk about a logarithm in general and have a branch card like this. And always say, okay, I want the principal or the argument be between alpha and here is alpha and going the other way. So if you do that, then again, derivative will exist and will be 1 over z, okay? Because this argument with this branch card will be continuous. So that's a very fine point when we are dealing with logarithm and its derivative. Okay, next, I'm going to take you to college algebra. When you first encountered exponential stuff. So you have a number, a positive number, all right. The first thing we did, we defined what do we mean by a to the n when n is a natural number. When n is a natural number, you simply multiply a n times by itself. So then we expanded this. We made it a little bit more by saying that, you know what? A to the 0, oh, here is n is a natural number. It's not 0, but we consider a to the 0. We want. All right, what next? Next, you want, of course, to define what do we mean by a to the negative 5. Well, then n is negative natural number, then we defined a to the negative n to be this. All right? Okay. So in this fashion, we define exponent when exponent is an integer. I have 5 to the a to the 5, a to the 0, a to the negative 4, or negative whatever. All right. So here is how we treated exponents. Then the question was, okay, we defined a to the n for an integer. How about for a rational number? How about this? Well, after discussion about square root, or in general, kth root or mth root, we said, you know what? We define this to be a square root of 2 to the third. The numerator will be the power. And in this fashion, we expanded the concept of powers to rational numbers, to this. So if you have p over q, so it is qth root of a to the p. Well, rational numbers is fine, but what about irrational numbers? How about, for instance, how do we define 5 to a square root of 2, which is an irrational number? Okay. Well, or in here, after learning about exponential function, here is what we did. We define a to the square root of 3, or any rational number, to be this. All right, the square root of 3 times logarithm of a in the exponent. So the generalization of the powers could not be achieved without knowledge of exponential function. So that is the significance of exponential function. In general, this is what we did. Of course, this part we did in calculus after learning about exponential function. What is a to the x? It's right here. What is, for example, the square root of 5 to the square root of 2? Well, we say this is equal to the square root of 2 exponential function, the square root of 2 natural log of the square root of 5. This is called general exponential function, right? X is not restricted. X is not restricted. Now, we are going to Do the same thing in complex. In complex, I'd like to introduce the general exponential function. Something like this. You have an complex number to another complex number sitting on as exponent. How do we define this? Well, we will follow the same thing that we did in calculus. After learning the exponential function, we define z to the alpha to be e to the alpha logarithm of z. Okay, good. Let's have some examples. This is called general exponential function. Let's do this. Find all values of this. Why I am saying all values? Because we are dealing with logarithm. If it is simply logarithm, has infinitely many solutions, unless you say principal value. Then you will have one output. Okay, we already found the log of 1 plus I. It's right there. And this is when I say infinitely many because of this k. So this is log of 1 plus I. Replaces this one right here. So it will be e to the I times this. When you multiply by I, this will be negative. This will be I log. And remember, k is an integer. K is an integer. Oh, well, it makes sense to see this is like e to the x plus iy. So here is e to the x. Since k is an integer, we replace it by negative k, that's fine. But what about this? E to the I theta. E to the I theta using Euler's theorem, it'll be cosine of theta plus I sine of theta. Okay, so what I sort of skipped a step here. Maybe I should go ahead and do it. So this is equal to e to the 2k pi minus pi over 4 times e to the I log of a square root of 2. Okay, this is it. All right, that's it. Any comment, any question for this general exponential function? Right. All right, thank you, Patrick. Thank you, Dawson. Where does e to the negative pi over 4? Where does the negative go for? Okay. So, yeah, it's a good question. It's a good question. You know, this was actually negative, right? here negative pi over 4, negative 2k. Well, this I pi over 4 for the logarithm, you multiply it by I, extra I. So you write this as I times log of 1 plus I. After finding log of 1 plus I, you multiply by I. So here is log of 1 plus I. Now we will multiply by I. If I multiply by I, this will be negative 1, I squared. And you will have I here. And that's what happened. So this is this negative pi over 4, negative 2k pi I is here. And here I square root of 2. Okay? Now, you might say, what happened here? Why this became positive? Because, when k is an integer means these. Okay, and so forth. Negative k also is the same thing. Negative k also will cover here minus plus, doesn't matter, right? And so forth. So if I know that here k is an integer, well, I know that if I replace k by negative k, again, I will cover all integers. But it looks a little bit better without that negative. It looks a little bit better. So that is how it worked. Okay. You're welcome. So that is, let's see. Here's another example. I want to compute. Oh, this time it says find principal value. So for general exponential, you have sometimes a lot, infinitely many values when this k is involved. But you have also principal value, which just the output is one quantity, just one. All right, to begin with, a complex number to power of another complex number is e, I, logarithm of I. Now here I am putting the principal value. The principal value of I, okay, here is I. I need logarithm of I. Remember, here is I. Its modulus is 1. Its principal argument is pi over 2. So the principal logarithm of I will be natural log of 1 plus I over pi over 2. I times pi over 2. Well, log of 1 is 0. Forget about this. This I and this I will give you negative. So we found the value of I raised to the power of I. Interesting enough, it's a real number. e to the pi, negative pi over 2. Okay, e to the negative pi. Any comment? Any question about this very fascinating example? A complex number raised to the power of another complex number. This is what we call the general exponential function. Okay, all right, let's see. I think that's all I wanted to say today, but so remember, yeah, we did this one. Good. Well, here is another example. Why not? Let's do another example. After all, in your next test, you are going to have examples, questions like this. I will ask you to find either all values or principal value. Okay. So for this one, definitely we need logarithm of 1 plus I, which all values of logarithm is right here. And then you say, look, 1 plus I to the 1 minus I is e to the this times log of base. This is log of base. I'm just using that definition of general exponential. Here is general exponential. So this is e z log of base. So this is e to the this exponent times log of base. Well, you multiply it out. It's a multiplication of two complex numbers, all right? You multiply this out, you are going to get this after simplifying. This is the in the exponent in here. This is the real part. This is the imaginary part. So this is the answer. Okay. Any comment, any question? Thank you, Ronald. Thank you, Patrick. Thank you, Corey. So I finished covering chapter 13. As I said, it is good to know what we did overall in chapter 13. We introduced complex numbers. We established some sort of algebra among complex numbers. I introduced functions of complex variable, right? Like polynomials, like e to the z, like trig functions. And then we also talked about derivative of complex functions. derivative of complex functions, all right? We notice that those very famous functions like e to the z, sine z, cosine z, they are entire function, meaning that they have derivative everywhere. Then when it comes to, of course, polynomials, the same thing. And we have all those rules of differentiation. We have product rule, we have quotient rule, we have, name it, this chain rule, right? We have all those rules valid. When it comes to logarithm, since log has infinitely many results, we cannot talk about derivative of log in general. We need to make it single value to talk about its derivative. And that is when we considered the principal value of logarithm, okay? And the principal value of logarithm has derivative everywhere except on the negative direction of x-axis, except, of course, zero included. No derivative at zero and no derivative at negative numbers. Okay, that was overall what we did in chapter 13. And in chapter 14, I'm going to talk about integration. Any comment? All right, so if you don't have any question or comment, I will stop at this point and we'll consider section 14.1 next Tuesday. Have a good day, everybody. Thank you, Michael. Thank you.